Hello everyone, good evening. And let's start now. So yesterday we had seen about the logistic regression, and today also we'll be seeing about the classification algorithm. And the aim is to cover two algorithms. One is the support vector machine and another is your KNN, K nearest neighbor. So let's start now. First of all, let's talk about this KNN. So this is the KNN, okay? The K nearest neighbor. And it's a supervised learning. It's a supervised learning, and this is particularly used for the classification. And you know that when you will be applying the classification, when your voice, that is the output variable, is categorical or discrete, at that time you'll be applying the classification algorithm. Now, so we are just going to discuss about it, and so here, first of all, let's talk about this nearest neighbor classifier. And you know that we are going to classify an input, whatever input will be given, and on the basis of that input, will be predicting about its output, that what to which output it exactly belongs to. Yeah. So, for example, if you just ask about this problem, and you know that here, what is happening, that we have a data set which consists of 0 to 9 digits. Means a digit may be 0 or the 1 or the 2 or the 3, kind of, up to 9. So I can say that it's a 10 class classification because we have 10 different digits. We have 10 unique digits, 0 to 9. Okay. So when suppose this 4 is input, suppose this 4 in we have input, now to which class it will classify? Will it belongs to 4? Will it belongs to 2? Or will it belongs to 1 and all? And you know that if the prediction will be correct, if the classification will be correct, then obviously this will be classified as 4. So how do we do that? In this K nearest neighbor, the K is what? It is a regularization term. It is the regularization term, and it may, if you are saying K equals to 1, so it will become 1 nearest neighbor. When it comes to 1 nearest neighbor, so how exactly we do? Try to understand. Suppose these are the two classes we have. All the data points belongs to either of these class 1. Either they will be they are from pink class, or another is blue class. Yeah. So here you see that we just input one feature. We are just trying to test one feature, and we try to predict the class for this feature. And this data point that we entered, what we will do now, we'll just measure the distance of all the data points to this input. We'll be measuring all the distance. And we find out that this particular data point is near to my new input. Okay. Since we are trying to find out the one nearest neighbor classifier, so we'll be trying to find out only one data point, which will be the most nearest data point to the new input. And in this case, you see that this is the most nearest data point to our input. Okay. And since it belongs to ping class, and that is why this new input that we have entered and to classify, it will also belongs to ping class. Yeah. So it is called as one nearest neighbor. Why one nearest neighbor? Because here we just try to find out only one data point, which is the most nearest neighbor to your input. Now let's talk about the two nearest. So in the two nearest, when you're taking the value of k as even number, so what will happen? There might be a chance, there might be a probability where point to this new input. And unfortunately, what has happened? Out of this two, one belongs to the blue class family and another belongs to pink class family. Okay. So in this way, what will happen? There's a tie. Whenever there will be a tie, then there is always a chance that you may get misclassification. Yeah. Suppose you see that this new input, actually it should belongs to pink class family, but there's a tie because we got two most nearest data point here. One belongs to blue and one belongs to pink. Yeah. So whenever there will be a tie, there will always be a probability that your model may do wrong prediction. Your model may do wrong classification, just like here. Okay. Yeah. All right. So that is why what we do, we always used to take the value of k as odd number of k. Because whenever the value of k will be odd, then there will always be, there will not be a chance of getting tie. And because just because of this tie, your model may do a wrong classification. Okay. Now, let's talk about this three nearest neighbor. So here what we did, we just give the value of k as 3, odd number. And in the odd number, this kind of problem will never be there. And suppose we input a new data point and we found that we just found 3 data points which are most nearest to it. Out of that, you see, 2 belongs to blue class and 1 belongs to pink class. So to which class this new input will be assigned, everyone? So it will be classified as blue class. Yeah, because out of this 3, 2 belongs to blue class. Again, although it should be 7 nearest, not the 8 nearest, because the 7 data point we have taken. So this should be 7 nearest. Now what we are doing, we are trying to predict an input on the basis of the 7 nearest neighbor. Means we'll be finding out the distance of this new data point to all the data points, and we'll be taking 7 data points which will be nearest to this new input, and then out of the 7 we'll just try to find out that where is the majority. So you see, for example, in this case, you see, out of the 7, 4 belongs to pink class and 3 belongs to blue class. So automatically what will happen, this new input will be classified as pink class. Okay. I think somebody has arrived now after 15 minutes. But you know, whenever you people arrive late, 10 to 15 minutes, somewhere it disturbs the class. So guys, please try to attend the class on time. Okay. So in this way, what we do, we just go with the odd number of value of k. So I can say that here, the k is what? It is a regularization term. It is the regularization term to manage the complexity of your model. Yeah. Okay. Now, please try to understand here. So here k is what? It is a regularization term. So whenever you increase the value of k, what happens? Your train accuracy will be increasing and your test accuracy will also be increasing. But after a certain point, what will happen? You see, your train accuracy will still keep increasing, but your test accuracy will start decreasing. So whenever your train accuracy will be high and the test accuracy will be low, what kind of model we will have, everyone? Overfitted? Yeah. So I can say that after certain value of k, what will happen? Your model will start creating overfitted region. So these are the overfitted region. So what we will do, we'll just find out the value of k where the training accuracy and test accuracy will be very high, and there will be very less difference, or I can say that they will be very close to each other. Okay, they will be very close to each other. For example, you just consider this sample data. Okay, in this sample data, what is there? We have ingredient, we have sweetness, we have crunchiness. So we have these 3 input, and on the basis of that, what is the food type? Okay, what is the food type? So suppose the ingredient is apple, the sweetness is 10, and the crunchiness is 9. So what does it mean? It means the food is fruit. So we just plotted it on the plot and say that we have just clustered them into 3 classes: the vegetable, fruits, and the produce, because you know that we have these 3 classes. Now, suppose new input is given, and that is tomato. So what is the challenge for us? We have to assign the appropriate class to it and say we are working on 5 nearest neighbor. So what is the meaning of 5 nearest neighbor, everyone? Anyone? That means out of this all, what I mean, what I try to find out, that just I'll be finding out 5 data points which are very near to this tomato. Say out of this 5, I found carrot, celery, and say lettuce, apple, and say bacon. You see, so out of this 5, you know that 3 belongs to where? 3 belongs to vegetable class. 1 belongs to protein class. 1 belongs to fruits class. So obviously what will happen? The tomato will be classified as what, everyone?
Vegetable.
Vegetable. Okay. So it will be classified as vegetable. And in this way, we actually work with the KNN. And I tell you one thing, guys, even if you see here, I can say that you can say that the supervised form of your clustering is what? It's a k-nearest neighbor. Where by grouping your data points, you just try to classify the new input. Okay. Now, as I was telling again and again that the new input that will be entered, its distance will be measured to all the remaining data point. So I tell you, just to measure the distance, we usually follow what? Euclidean distance. The Euclidean distance we used to follow to measure the distance between the two data points. Okay. All right. So this is the theoretical aspects of your k-nearest neighbor. Okay. So let's see here, guys. We are just reading this data, WBCD, and you see we have 569 rows and 32 column. Just for a revision purpose, if I ask you, if I want to reduce the number of column, then what is the option you have, everyone? Suppose I just want to reduce the number of column from 32 to say 17 or 18. What is the option you have?
PCA.
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 Yeah. Or we can do feature selection. Now, if I see here this WBCD, actually this is the cancer data where on the basis of the several input features like radius mean, texture mean, perimeter mean, to which class this diagnosis will be assigned to. Okay, so on the basis of this this radius, on the basis of this radius or these features, if these are the features in the first row, what is the class of the problem? So the disease will be diagnosed as benign. The cancer will be diagnosed as benign. So how many unique values are there in this diagnosis? So either you can use this value underscore counts and it is saying that benign and malignant. Or what you can do, you can call the unique function. It will tell you that there are two, benign and malignant. Okay. Now here what we are doing, try to understand, just to make more readability, we are just renaming this B as benign and M as malignant. So you see what exactly we are doing. So we are calling this np.where, and we are saying that wherever you find out this diagnosis in the diagnosis B, replace them with benign in the same column, in the same diagnosis column. In the same way, wherever you find out this diagnosis as M, just replace them with malignant in the same column. Now if you see, this B has been benign and M has been malignant. Okay, I hope that makes sense, everyone. Now, let me see the value counts. So you know that it is benign and malignant. So we have 357 as this one. If I ask you, friends, do you think that just to diagnose this cancer, do you think that this ID will have any statistical significance?
No, sir.
No. So what should I do? I should just drop it. I should just exclude it. So that is why what I have done here, I'm just creating a data where I'll be selecting all the rows, but the columns will be starting from the index number 1, because at the index number 0, we had what? We had ID column. Okay. Now, second thing, if I describe my data, so you find out that there's a scaling issue. You see, one where the radius of the mean of the radius is 14.12, mean of the texture is 19.28, but the here it is 91, it is 654. So there is a huge difference in the mean value. So whenever you find out the huge difference between the mean value, what is the meaning of that? Your data is suffering from a scaling issue. And
Yes, sir.
the solution to this scaling issue is what? Either normalization or standardization. So here what we have done, we have just defined a function, and this function will be doing min-max scalar. You see, I minus I dot min upon I dot max minus I dot min. So it is performing min-max scalar. And what we have done, we are just applying this function on our numeric data. And you see, after applying this normalization, all the columns mean value has become 0 and the max value has become 1. Okay. Now, what we are doing, we are just segregating our data into X and Y. We are just segregating our data into X and Y. And you see that the WBCD underscore N is what? It is the numeric data. And it was consisting only the input variable. So we took them in the X, and the diagnosis we took as a Y. So again, after that, what we have done, we are just splitting our data into train and test. And what is the proportion of test? It is 20%. Now, after that, this is really very, very, very important. So everyone, first of all, you see what we have done. Let me tell you. If you just recall this slide, if you just recall this slide, so what we have done here, everyone. Now, first thing, again, if I explain this in another way, so I will tell you that just forget about this reason. I know that this is the reason where your model will be getting overfitted, but what is our aim? We just try to find out this value of K. We just try to find out this K where your model will be best right fitted. When I'm saying that best right fitted, that means where the train accuracy and test accuracy both will be very high and they will be very close to each other. So now if I have to say that, then I can say that here I'll be trying with the different value of K. I'll be building the model with a different value of K, and then I'll be checking out that at which value of K my model is performing best. Yeah. So that means I'll have to build this model for multiple value of K. And that is why you see here that we took this empty list ACC. We just took this empty list ACC, and then here we are starting from 3. Why we are starting from 3, everyone? Just to take odd value of K and just to start from the 3 nearest neighbor classifier. So here we are building the K nearest neighbor classifier, and we are saying n underscore neighbors equals to I. What is the first value of I? 3. And it will be reaching till when? It will be running till 49, isn't? If I say this range function, then it will be starting from 3. It will be running till 50 minus 1, 49. And what will be the gap? 2. So whenever you'll be starting with 3 and you'll be getting the value of interval of 2, so can I say that it will be taking the odd value of K starting from 3? So say we just built this K nearest neighbor classifier first when the n underscore neighbors equals to I. Means the first model that we built, it was 3NN, 3 nearest neighbor. Now, this 3 nearest neighbor will be trained on what data? On trained data through fit function. And then what will happen? It will be calculating the train accuracy and test accuracy. Okay. And this train accuracy and test accuracy will be appended in what? In the ACC list. Okay. So what we will do in this way, we'll be trying to build the model for 5NN, 7NN, 9NN, 11NN. And for each nearest neighbor, we'll have some train accuracy and the test accuracy. So what is our criteria? We'll be trying to see that value of K where the train accuracy and test accuracy both will be very high and they will be very close to each other. So for example, when I ran this problem, let me check. So I got this ACC. And you see, so this is my training accuracy and this is my test accuracy. Next. So we are just plotting a plot. And for that purpose, what we are doing, In one line plot, we will be taking the value of k from 3 to 49. Yeah, we are going to see the I0 for I in ACC. This ACC is containing two items. So I0 is what? It is the train accuracy. So I can say that this train accuracy we are going to represent with R. Then the another is what? Test accuracy. So that test accuracy we are going to plot with the line plot with blue color. Please mute. Okay, everyone. Please try this. So here, we started with the value of k from 3. So you see, Mr. Dhruv, please mute yourself. Mr. Dhruv Porus, please mute yourself. Whenever it will require, you can unmute yourself, but by default, please be muted. So now you see, these are the value of k, and there's the interval of 10. So from where the train and test accuracy are high and close to each other. So if I talk about this one, can I say that here the train and test accuracy both are very close to each other? Guys, do you agree? And you see that both of them are more than 96.5%. Both of them are more than 96.5%. So according to me, this is the best value of k where you'll be getting the right fitted model. Now, even you see, if you consider this one, you see here that the train accuracy is 99 and the test accuracy is somewhere 96.6 or 7. Okay. So although both of them are very good accuracy, but if you find out the gap between them, then it will be somewhere around 2.5 or 3. Okay. So whenever we'll be trying to get the best right fitted model, first primary requisition will be that both of them should be having high accuracy. And what is the second requisition? So the second requisition is that they should be very close to each other.
Sir, what about that point which is at 98 and 97.5?
Where? This one. Actually, see, this is where I think k is equals to 3. This is where the k is equals to 5. This is where the k is equals to 7, 9. This is what? 11.
Yes, sir, that 9 part.
9 part. This one you are talking about. This one, huh?
Yes, sir.
Okay. What is the difference here? I think 0.5, no?
Yes, sir.
And
that is two very close now.
Yeah. See, according to me, when I am considering, so I am considering this one. So here my priority is what? That they are very close to each other. Can I say that at the k equals to 13, the train and test accuracy are very close to each other in comparison to k9? But, and another, what is my perception, dear, please try to understand. I think that there's not much difference between the 96.5 and 98. I think that there's only a 1.5% difference in the accuracy. But when I look at their differences, then the differences is negligible. But yes, I totally agree with you. You can opt k equals to 9 also, because they will also be considered as very close to each other. Although in comparison to 13, they will not be considered as very close to each other. But the positive aspects with this k equals to 9 is that they have larger accuracy in comparison to when you are taking k equals to 13. So it's up to you, dear. Even if you say that I'll opt k equals to 9, I 100% agree.
Okay, sir.
Okay, yeah. So let's finalize and say that I'm finalizing with the k equals to 13. And you see earlier it was 19. So let's say I'm just finalizing it with the k equals to 13. Okay, now if I see the accuracy underscore score, so it is what? 96.49. Yeah. So the train accuracy is what? Test accuracy is what? 96.49. And if you want to check the confusion matrix, then you can check it. In the same way, let's talk about the train accuracy. That is 96.7. So can you see here, when you were taking the k equals to 9, so the difference was around 1.5, isn't it? But here, the difference is just only 0.3, 0.003. So that's why, again, it's your call, whichever model you want to choose. Okay. So this is the k nearest neighbor. This is the k nearest neighbor. So guys, let's do one thing. All right, everyone. So let's start support vector machine.
Sir, I have a doubt.
Yes, Yuvraj.
Sir, when you just showed us the line graph, how did you classify them like K9, K13, etc.?
Actually, see, that is, see. Try to understand here. When you are plotting this line, plot, you have taken at the x-axis, what value you have taken? From 3 to 49 at the order of the interval of 2. So this is what? This is actually the k, the value of k. Okay. In the same way here also, you see, you have taken the value of k, starting from 3 till 49 with the gap of 2. So that means there will be 3, 6, and 9.
Yes, sir.
Isn't? So if I take this train accuracy and test accuracy, if I connect them, and if I go here, Then they go to what? 3.
Yes, sir.
So the value of k is what? 3.
Yes, sir. Now I understood.
Yeah. If I connect this, so that is 6. Is that clear now?
Yes, sir.
Okay. Let's talk about the support vector machine now. Yeah. So we are trying to again do this SVM. And one more thing I'll tell you guys, this SVM can be done for the regression and classification both. This SVM can be done for classification and regression both, but yes, mainly it is known for classification, first thing. Second thing is that when it comes to this SVM, then this SVM is done for 2-class classification. It is effectively used for 2-class classification, but again I'm telling you that it does not mean it cannot work on multi-class classification. But what it do, it actually convert this multi-class in the form of 2-class and then do classification. So I'll show you how. Okay. So what is this support vector machine? In this support vector machine, you just consider this one. So say that we have 2 classes, you have 2 category of the output. One is the circle, another is the square. So what will be our agenda? We'll be trying to put the hyperplane, in between them in such a way that on the either side of the hyperplane we will have a square and another side of the hyperplane we will have circle. Okay. And you see, now suppose this is the class we have and we are trying to put the hyperplane between these 2 classes. So we can put them on the 3 bases. One is what? You see this one, which is the A, another is B, another is C. So we have to finalize that which hyperplane will be the best one. So when I consider this A, so here you see that this and this, they are very near to your hyperplane and there might be a misclassification and they can jump to the another side of this A. Yeah. So might be that this square can jump to this side and this can be jumped to this side. Means they could be misclassified. In the same way, if I take this C, in this C, although these squares are having significant distance from this hyperplane, but if I consider this circle, then I can say that this particular circle is very near to this hyperplane. So there might be a chance, there might be a probability that can jump to another side of C and it could be misclassified. Okay, now if I see this B, so this B is the hyperplane which has been placed in between this in such a way that all the classes are having significant distance. All the classes are having significant distance, and that's why if we have to choose, then we can say that this B is the best fit hyperplane to classify these two classes. Next, whenever your circle will be misclassified or your square will be misclassified, so it's an error. Next, see, it is not possible that always you are going to get a linearly separable data, just like we have seen till now. Suppose you're so what we can do, whenever you will have non-linearly separable data, then the first option is you need to convert them into linearly separable. So before applying the KNN, before applying this K nearest neighbor, you need to first convert this non-linearly separable data into what? Into linearly separable. Okay. You need to convert them into linearly separable. Okay. Yeah. So how this non-linearly separable data will be converted into, how this non-linearly separable data will be converted into linearly separable. So that will be done through kernel trick. That will be done through kernel trick. So what will happen? First of all, your kernel trick will be converting your non-linear data into linearly separable, and then you can apply hyperplane between them to classify. Okay. So these kernel tricks are really very important whenever you will have non-linearly separable data. Let's see now. So when it comes to this kernel trick, then you see we may have the linear kernel trick, we may have the polynomial, we may have the sigmoid or Gaussian RPF. See what happens, suppose you know about the pattern of your data, that what kind of data you have. If you're already aware that you know that your data is linearly separable, you just use linear kernel, and this is your default. If you know that the pattern that your data is following, it is somewhere sigmoid curve, so you just use sigmoid kernel. If the pattern is kind of U-shape or the hyperbola, you just use the polynomial. And if you're not aware, then what you can do, you just use this Gaussian RBF kernel. But the thing is that suppose if I'll have to do, so what I'll do, I'll just try by all the kernel trick. I'll be building my model with all kind of kernel trick we have, and then whichever will be giving me the best result, I'll just finalize them. Yeah. So in this way, what will happen? The prediction will have the higher accuracy and the error will be less. Now, as I was saying that your SVM is used for binary classification, but it does not mean that you cannot do the multi-class classification. But in that case, you need to come up these multi-class classification in the form of the binary classes. Suppose that we have these 4 colors: green, yellow, red, and blue. So these are the 4-class classification. So if you want to apply the SVM on it, then first of all, it will be converting them into binary class. So how it will do? So we have two options. One is one versus all. In this one versus all, what we'll be doing, at one side of the hyperplane will have only one color, and at the another side of the hyperplane will have all the remaining classes. See, so here we just took green at one side and the remaining at the another side. In this, we took yellow at the one side and remaining at the another side. Here, we took red at the one side and remaining at the another side. In this way, what we have done, we just converted your multi-classes into binary classes. Another thing is that you will have four. Let's do the combination of two. Let's do the combination of two out of this four. So you know that it will become now combination problem, NCR, and here it will become 4C2 because total classes are present 4 and the combination that you want 2. So it's a 4C2 problem, and the formula will be applied as n into n minus 1 upon 2. So 4 into 3 upon 2. Yeah. So how many combination will be there? 6. So when you will have 4 multi-classes, and if you want to get them in the form of combination of 2, then 6 combinations will be made. Then 6 combinations will be made. And in this way, you had taken the multi-classes into binary classes. And the second thing is that you will just take the combined prediction of them. All right. So this is all about the support vector machine. Now, one more thing I tell you about the black box models. Black box model means you don't know the internal working of the model, how they're performing. You just suppose this is your model, you're providing input, you're getting prediction. But what exactly is the internal processing, you're not much aware. So it is called as black box. Let me show the implementation of it. Okay. So suppose we are just reading this data, and this is the later data. And you see, in this later data, the later is the output variable. The later is the output variable. And if I see the unique values, if I see the unique values in this later column, so letters, later, dot unique. So how many alphabets are there? 26 here. Means it's a 26 class classification. So now you can understand what it will do. It will first convert them into the form of in the pair of 2. And then after, it will do classification. Let me find out the describe function. So I think that the normalization is not needed here because there's not much difference in the mean value of the data. Now, let's build this model, and you see, since you have to perform the classification, and that's why from sklearn.svm, you are taking SVC. Yeah, you're taking support vector classifier, and you're importing train test spread. Next, then you just splitted your data into train and test. The size of the train is 20%, and the size of the test is, sorry, the size of the train is 80%, and the size of the test is 20%. And you see the total data you had 20,000, and out of this 20,000, you got 16,000 for the training purpose and the 4,000 for the testing purpose. So what you are doing right now you are segregating your train and test into input and output also. And you see here that in this data, the first column is what? It is the output. You see, the first means the zero index is what? The output data. And that is why you have just taken in the X all the columns starting from the index number 1, while in the Y we are taking the 0th index column. Okay. Next. Now, what we will be doing, we'll be building the model. So first model that we are building, it's a support vector classifier. And here, what kernel trick we are using? We are taking linear kernel trick. And then we are training this model on the trained data, doing prediction on the test data, and finding out the test accuracy. And how did we find out this test accuracy? So wherever your predicted value will be matched with the test data, it is correct classification. So we'll be just finding out them and we'll be taking the mean of it. Okay, so you see the test accuracies are what? 85.625. Even if you want to check the confusion matrix, then it's a confusion matrix of the multi-classes. Now, we will check for the RBF kernel also. So here you see in this kernel now, instead of this linear, we have written RBF. You see, when we took this RBF kernel, it is giving us 92.97% accuracy for the test data. Let's do it for the polynomial also. So when we took this kernel equals to polynomial and the other remaining things are same, and when we built on this, so we just tried with it polynomial kernel, and what is the test accuracy we got? 95.2. So let me make a dictionary where we'll have two two key. One is model, another is accuracy. And in the model, we just kept all the so it is 85.62, it's 95.2, and what about this? $92.97. Okay, so when I visualize it, you see. So out of this, what do you think, friends? Which model is the best model?
Polynomial, sir.
Polynomial, because it is giving us 95.5% accuracy. Yeah. So in this way, we just work with the support vector machine. All right. So this is all about the support vector machine. Now, if you have any question, then you can ask me. Otherwise, we'll just stop here.